Section: Introduction. In this section, we discuss the increasing concern about ensuring the safety of LLM outputs. We have observed that even though models are trained to provide helpful and honest outputs using methods like RLHF, there is a rise in attacks against these models that can bypass existing defenses. To address this, various defenses have been proposed, some of which rely on expensive algorithms, model fine-tuning, or proprietary APIs like the OpenAI Content Moderation API. We present a defense mechanism against adversarial attacks on model alignment using self-evaluation. Our approach shows that pre-trained models can accurately classify inputs and outputs as safe or unsafe without the need for additional fine-tuning. This classification holds true even for inputs and outputs with adversarial suffixes. By leveraging another LLM to classify inputs as safe or unsafe, we can significantly reduce the OSR of attacked inputs from 95.0% to 0.0% for Vicuña 7b. Our method outperforms existing defenses, especially in identifying harmful samples with adversarial suffixes that other methods struggle to classify correctly. By separating safety classification from generation, our defense proves to be robust against adaptive attacks, outperforming commercial moderation APIs and other defense mechanisms like LlamaGuard 2. While it is possible to attack the evaluator, doing so requires training a specific adversarial suffix targeted at the evaluator. Despite this, our defense still achieves lower OSR values than an undefended generator. Our approach is easy to implement, does not require fine-tuning, and demonstrates superior performance across evaluation settings, making it a practical defense strategy. We consider a scenario where an LLM receives potentially adversarial queries and must generate safe responses. The adversary can only access the model's queries, allowing them to observe responses and manipulate inputs but not access the model's weights. A successful defense should balance utility and safety, responding appropriately to safe inputs and refusing to answer unsafe queries effectively. We acknowledge the presence of adversarial suffixes that can lead the model to generate unsafe outputs. These suffixes can transfer across different model architectures and inputs, posing a challenge to model safety. Our evaluation criteria focus on the combined performance of the generator and evaluator in identifying harmful inputs and outputs. By assessing the OSR and F1 scores, we can measure the effectiveness of our defense strategy compared to baseline defenses like LlamaGuard 2 and various content moderation APIs. Section Summary. In this section, we introduce a defense mechanism against adversarial attacks on model alignment using self-evaluation. We demonstrate that pre-trained models can accurately classify inputs and outputs as safe or unsafe without additional fine-tuning, even when attacked with adversarial suffixes. Our defense method outperforms existing defenses like LlamaGuard 2 and content moderation APIs, showing high accuracy in classifying harmful samples and being challenging to attack in adaptive settings. Section: Self-evaluation as defense. In this section, we rely on model self-evaluation as our defense strategy. We use a model E to assess whether the content generated by the chatbot pipeline, consisting of G and E, is harmful or not. If the content is deemed harmful, the system will refuse to provide an answer. On the other hand, if the content is safe, it will be returned to the user. We explore three defense settings: input only, output only, and input-output (IO). In the input-only defense, E evaluates only the user prompt X. This is a quicker and more cost-effective evaluation method, as harmful prompts can be identified early on, preventing them from reaching G, and there are fewer tokens for E to evaluate. In the output-only defense, G generates a response Y to the user prompt X, and E evaluates only Y. Although this may incur additional costs if G generates harmful responses, this approach shields E from direct user input, potentially making it less vulnerable to attacks. In the input-output defense, E evaluates both the prompt X and the output Y, providing the most comprehensive context for determining harmful content. However, this setting is the most resource-intensive for both the evaluator and the combined G and E. We present the results of our defense across these three settings and evaluate them under different attack scenarios. Our defense significantly reduces the susceptibility of all models to attacks, bringing the ASR, attack success rate, close to zero for all evaluators, generators, and settings. Our self-evaluation approach outperforms existing evaluation APIs and Llama Guard 2, demonstrating its effectiveness even with smaller, open-source models. We also examine the impact of evaluators on safe inputs to ensure that the addition of an evaluator does not decrease the response rate of the generator on safe inputs. Our findings show that self-evaluation does not harm performance on safe inputs and effectively reduces the ASR for unsafe inputs across all settings. Section Summary. In this section, we introduce a defense mechanism based on model self-evaluation, where a model is tasked with determining if generated content is harmful or not. We explore three defense settings: input only, output only, and input-output, each offering different levels of evaluation complexity and cost. Our self-evaluation defense proves effective in reducing the susceptibility of models to attacks, outperforming existing evaluation APIs and demonstrating the feasibility of this defense approach even with smaller, open-source models. Section: Attacking the Evaluator. In this section, we explore how vulnerable the defenses we discussed earlier are to attacks. We question if it's possible to attack both the evaluator, E, and the generator, G, simultaneously. The input-only defense seems to be easily attacked because both E and G receive the same input, making it possible to append a suffix that can target both. We introduce a new attack called the direct attack, where we train a suffix to target both the evaluator and generator. We show that even though it's possible to successfully attack input-only and input-output defenses using the direct attack, a model defended with E_I still has lower ASR compared to an undefended model. When formulating the attack, we focus on scenarios where the adversary can only control the input. Instead of inserting a suffix, S_G, that attacks only the generator, we consider inserting a suffix, S_GE, that can attack both the generator and evaluator. Attacking the evaluator differs from attacking the generator because the evaluator can make mistakes in two ways: by classifying unsafe inputs as safe or safe inputs as unsafe. We concentrate more on the former as it poses a higher risk. We assume the adversary can only observe the outputs of G when E marks them as safe and can always infer E's classifications. To find an attack suffix, we explore different methods. The first method involves concatenating two separate suffixes, S_G and S_E, that are fine-tuned to attack the generator and evaluator, respectively. The second method optimizes one suffix for both the generator and evaluator objectives in turn until a balance is achieved. The third method optimizes one suffix for both the generator and evaluator simultaneously by considering their respective losses. When we test the concatenation method, we find that the combined suffix can successfully attack both the generator and evaluator. However, the ASR is significantly lower compared to only attacking the generator for all evaluators. We observe notable drops in ASR for the generator when using the combined suffix optimized for both the generator and evaluator. We also notice that self-evaluation is a stronger defense than the generator's own mechanisms. When we evaluate this attack on different models and APIs, we find varying levels of susceptibility. In the optimization in turn method, we train the suffix as a whole, optimizing it for the generator and evaluator objectives in turn. This method results in a less effective attack compared to concatenation. Overall, while these methods can still successfully attack the models and APIs, concatenation proves to be more successful than optimization in turn. Section Summary. In this section, we explore attacking both the evaluator and generator simultaneously, focusing on the susceptibility of defenses to adversarial attacks. We introduce a direct attack method that trains a suffix to target both the evaluator and generator, demonstrating successful attacks on input-only and input-output defenses. By testing various methods to obtain the attack suffix, such as concatenation and optimization in turn, we observe that the concatenated suffix optimized for both the generator and evaluator proves to be a stronger attack compared to optimization in turn, showcasing the effectiveness of attacking both components together. Section: Single Objective Optimization. In this section, we discuss single objective optimization and the copy-paste attack. Single objective optimization is a powerful attack method that can significantly impact the performance of models like Llama 2 and Vicuña. It is more effective in the input-only setting compared to other approaches, notably increasing the OSR of these models. However, in the input-output setting, it is generally weaker than concatenation. Interestingly, single objective optimization is the only method that successfully attacks GPT-4, raising its OSR from 0.0 to 10.0. These results highlight that attacking the evaluator in different settings is feasible, but self-evaluation defense does not necessarily make the generator more vulnerable to attacks. It still provides a substantial level of defense, although some API evaluators may be exceptions. Moving on to the copy-paste attack, it is designed to test the output-only defense. This attack leverages the instruction following capabilities of language models, LLMs, and involves appending a specific suffix to the model's output. The copy-paste attack can target both the generator and the evaluator, but similar to the direct attack, it is weaker against the generator. Our defense method surpasses other approaches, showing higher increases in OSR between generator-only and copy-paste attacks. However, the copy-paste attack can be challenging in practice, with varying success rates depending on the instructions given to the generator. Furthermore, our study reveals that existing defenses like Llama Guard 2 exhibit more variability in their classifications and are sensitive to changes in suffixes. On the other hand, the evaluators we tested consistently classify attacked inputs as harmful, regardless of the appended suffix. Our findings shed light on how adversarial suffixes can bypass generator alignment without compromising the model's ability to identify harmful inputs. Despite the potential for attacks on our defense method, it does not make models more susceptible to attacks. Self-evaluation proves to be a robust defense strategy compared to other methods, as indicated by lower OSR increases when under attack. In related work, harmful text classification and adversarial attacks have been extensively studied, with various approaches and methods proposed to address these challenges. LLM defenses like Llama Guard and Llama Guard 2 aim to protect model inputs and outputs, although they may require fine-tuning and could be vulnerable to attacks. Other defense strategies, such as filtering and inference time guardrails, have also been suggested to mitigate adversarial attacks on language models. Section Summary. In this section, we explore single objective optimization attacks, which prove more effective than other methods in the input-only setting, significantly impacting the OSR of Llama 2 and Vicuña. While weaker than concatenation in the input-output setting, this attack uniquely succeeds in targeting GPT-4. Additionally, we introduce the copy-paste attack, showcasing its ability to target both generators and evaluators, outperforming other defense methods and demonstrating the robustness of self-evaluation as a defense strategy. Section: Self-evaluation. In this section, we show that language models, LLMs, are able to predict accurately how likely they are to answer prompts correctly. Other studies have revealed that self-evaluation is a useful method in various areas of model performance such as decoding, representations, and reasoning. At the same time, researchers have discovered that models can detect harmful content through self-evaluation. However, there is a lack of comprehensive evaluation on attacked inputs for multiple models or comparison with content evaluation APIs.